Okay, so in this sequence of videos, we'll be following very, very closely the book by Griffiths, which is known as, it's called Introduction to Quantum Mechanics, and we'll be following very closely the third edition. Okay, so in this video, we are going to be talking about section 1.1. But before we start talking about this section, which is going to be very short, let's just discuss or mention some of the concepts that we usually learn when we are learning about quantum mechanics. So, one of these concepts is the wave particle duality. You may have heard about this if you took a course on modern physics. And a typical example of this duality is if you think about a light, for example. Sometimes when we are talking about light, we talk about photons, which are particles. But sometimes we also talk about interference effects, for example. And when we are talking about interference effects, we have waves in our mind. So, what is it? Is it a particle or is it a wave? So, that's the idea of the wave particle duality. This is very nicely discussed in a video, in a lecture by Feynman, which I'm going to put in the description of the video if you want to watch. If you prefer to read, there is also a text that you can write about this wave particle duality. In this lecture by Feynman, another concept that shows up is the idea of the uncertainty principle. The uncertainty principle says the following. Suppose we have, we can talk about different quantities, but suppose we have in mind position and momentum of a particle. And what the uncertainty principle says is that uh, the standard deviation of position multiplied by the standard deviation of momentum can never be zero. So what this is saying is that we don't have absolute precision when we make measurements of position and momentum. We cannot know exactly the position and momentum of the particle at the same time. This product will have to be larger than a certain finite value that we'll be learning about. Okay? So this is the uncertainty principle. We cannot know position and momentum at the same time exactly. And there are other variables also that follow this uncertainty principle. Also related with this equation that we just wrote, we have the idea that quantum mechanics is probabilistic. And so when we talk about the position or the momentum of a particle, for example, we talk about the probability that this particle has this or that position. And, and it's not because our instrument is not good enough. It's because quantum mechanics is intrinsically probabilistic. There is always some uncertainty involved. Okay, so I'm just mentioning these concepts. Okay, we are not talking about them in details. We will be talking about all of them much more in details, and all of these topics that I just mentioned here, we will be learning exactly in this first chapter one. Let me mention some other concepts. Um, one other concept that is very important is the idea of quantization. We talk, for example, about energy being quantized or energy being discrete, which is a strange thing to think about now in our daily lives when we are driving our car. We don't think about energy or the kinetic energy being discrete. We don't go from 50 miles per hour to 60 miles per hour in a jump. We go continuously. We go from 50 to 50.01 to 53.77. So we move continuously. But in quantum mechanics, we'll talk about energy being discrete, and there are other quantities that are also discrete that we'll learn more about. Okay. Um, One idea you may already have when we think about the photons that we just mentioned, we say that the energy of the photon is given by h. This h here is Planck's constant, multiplied by ni. Ni here is the frequency, So let's put here is the frequency of the light wave. When we say light in a loose way, what we mean here is electromagnetic waves. So when we have this equation, what we are saying is that the energy of the photons is quantized. Um, there are other interesting concepts, for example, quantum tunneling. You may have heard about, and we will hear more about it in this course. Quantum tunneling, energy being discrete, these are all topics that will be seen in chapter 2. There are other interesting topics as well. For example, the idea of superposition. Superposition, we can also mention about superposition in chapter 2. There is another concept of entanglement, which you may have heard about. This one we'll not talk about in this course, but we can discuss if you're interested. These two are very important in um, new developments, in what we call quantum technologies, such as the idea of quantum computer, which you may have heard about in the media, or quantum cryptography. So these are things that use these concepts. Okay, and well, there'll be other concepts as we move on, but I just wanted to give you an idea of these terms, uh, which you may already have heard of. Okay, very well. But as we said, in this first video, we'll be talking about section 1.1. So let's go start talking about our first section. As I said, we are closely following Griffiths' book. This section 1.1, is called the Schrödinger's equation. So let me write this name here. Schrödinger equation. Well, of course, if you don't know German, it may be hard to pronounce this name, but just out of curiosity, I have here a YouTube video to give you a sense on how this name is pronounced. So here it is, and I'm going to put for you to listen to, just out of curiosity.
Schrödinger.
All right, very well. So what is this Schrödinger equation? Is, in a sense, analogous or in importance or in use to, so let me put here, this Schrödinger equation is analogous in importance or in use to Newton's second law in classical mechanics. Okay, so in classical mechanics, you already learned about Newton's second law. We will review it here, but when we are talking about quantum mechanics, instead of using Newton's second law, we use Schrödinger's equation. Okay, so and that's the equation that we are going to be discussing. I'll be just presenting this equation here in this section 1.1. Okay, well, but let's start with Newton's second law, which you already know. So what is the idea? Suppose we have a certain object, a particle, a car, a person moving in one dimension. So that's why there is just a line here. So this object is moving. This object has a certain mass m. It's subject to some force. This force may depend on position and time. So with Newton's second law, if I give to you the initial position of this object, you will be able to get a later position of this object. How? Using Newton's second law. So what is behind that? What is this law? It says that force is equal to ma. A is the acceleration, m is the mass of this object. How can we rewrite this equation? Well, acceleration is the second derivative of position. So I can write here mass, and here the second derivative of position. If I can solve this equation, given a certain initial position, I will be able to find the position later in time. Very well. There is another way to write this equation, which is the following. If we are thinking about conservative systems, this is also a term that you probably, well, you must have learned in classical mechanics. When we are talking about conservative systems, we are thinking about systems that do not have any kind of dissipation, that do not have any kind of friction. And in these kind of systems, which are the only kinds of systems that we'll be learning in this course, okay, in these kind of systems, we can also write the force in terms of the potential energy. How? You must learn this, you must remember this equation, that the force is minus the partial derivative of the potential energy, the partial derivative in position. Why? Because this potential energy, again, can be a function of position and time. So that's why we have here a partial derivative. Now, this notation V for potential energy function, in previous course, you may have used the notation U, the letter U. Some books also use this notation PE from potential energy. Okay, in this book, the notation is V. So whenever you see V, think about potential energy. So the sum of the potential energy plus the kinetic energy gives us the total energy of the object. We don't have dissipation, as I said. Okay, very well. So we can rewrite this equation, which is the equation Newton's second law. We can rewrite it like this. Mass, second order derivative of position, equals to minus partial derivative of the potential energy. This, with this equation, if I give you the initial position, you will be able to find the later positions of the object. If we also give to you the initial velocity or momentum, you will also be able to get um, velocity and momentum later in time. And in fact, you'll be able to get any dynamical quantity, like the kinetic energy and any other dynamical quantity. So this is a very important, it's like the main equation when we are describing the dynamics of objects in classical mechanics, as you know, as you already knew. So this is the review that I wanted to give to you. This is something that you already knew. Let me cut this all. And then let me put here under Newton's second law, under classical mechanics, this equation that we just wrote, mass, second order derivative of x equals to minus partial derivative of potential energy. This is the main equation, one of the main equations when we are studying an object that is moving in one dimension, a classical object. Okay. What is the equivalent of that when we go into the quantum domain? The equation that is equivalent, which is what we said, the Schrödinger equation, is the following. I'm going to write this equation just as is given in the first page of your book, and then we are going to talk a little bit more about it, okay? So this equation involves I here is the unit, the imaginary number. I here is the square root of minus 1. Okay? Then we have h bar. H bar is equal to Planck's constant divided by 2 pi. And the value, of course, you don't need to know these things. No, you look at in a book or online, is 1.05 and some other digits multiplied by 10 to minus 34 joule second. Okay. In addition to that, we have here a partial derivative in time of, this is a Greek letter called psi. So I'm going to put my psi here. In Greek, it's actually called psi. This function is a function of position and time. Okay, this function is known as the wave function, and we'll be talking much more about it. Okay, but you see that instead of talking about position, we are talking about a function of position and time, a function, not the position directly. Okay, what else do we have? Uh, um, this is the left side of our equation. Now I'm going to write the right side of our equation. Minus, negative, that h bar square divided by 2 times the mass of the particle we study. Now we have a second order partial derivative, and now in x. And then comes the potential energy and again the wave function. This is Schrödinger equation. And this is the equation that will be seen throughout this course. All the problems I'll be solving will be using this equation. Okay? So what do we know about this equation? What do we know about this wave function? All the information about the particle, about the system, is when we are talking about a quantum system. So let me erase all this. So all the information about the quantum system is contained in this function, in the wave function. Okay, so if I want to predict where my particle will be later in time, I'll be dealing with this wave function, not with that equation that we saw before for classical mechanics. Okay, we'll see many more details about this equation. But when is quantum mechanics important? When are the quantum effects important? Well, not in our daily life. In our daily life, when we talk about bicycles and cars and people, we don't we don't think about quantum effects. Quantum effects are things that happen at the quantum domain, uh, things that are noticeable when we are talking about atoms or subatomic uh, particles, okay? The tiny world. Anyway, the important thing is the wave function, one of the important entities, and we'll be talking about it now in the section 1.2. So that's the end of section 1.1. The important thing that we discussed, didn't explain where it came from, but I just told you that is the important equation in quantum mechanics is Schrödinger's equation. It gives us, it's the equation that we need to solve to obtain this wave function, and all the information about the system, all the information about the dynamics of the system is contained in this wave function. So that's the end of section 1.1.